The properties exhibited by colloidal solutions can be classified as colligative properties, optical properties, mechanical properties, and electrical properties. Let us first discuss their colligative properties. Colloidal solutions exhibit the colligative properties osmotic pressure, elevation in boiling point, depression in freezing point, and relative lowering of vapor pressure, in the same way as true solutions do. However, the magnitudes of these properties for colloidal solutions are much smaller than those obtained for true solutions, and thus it becomes very difficult to measure them accurately. This is because colloidal particles, being bigger aggregates, have very high average molecular masses. Therefore, the number of particles in a colloidal solution is small as compared to that of a true solution. Hence, at a given concentration, the value of any colligative property of a colloidal solution is of a small order as compared to the value shown by a true solution. However, colloids exhibit measurable osmotic pressure, which can be determined with a reasonable degree of accuracy. This property of colloidal solutions is therefore used to determine the average molecular masses of certain colloidal particles, like proteins and other polymers. One property of colloids that distinguishes them from true solutions is the Tyndall effect. When a beam of light passes through a true solution, there is no scattering and the path of light cannot be traced. The solution appears clear if observed in the direction of light, and perfectly dark if observed from a direction perpendicular to the direction of light. On the other hand, when a beam of light is allowed to pass through a colloid, it gets scattered by the colloidal particles, and the path of the light can be traced. The path of light gets illuminated with a blush light. This phenomenon of scattering of light by colloidal particles is called the Tyndall effect. The illuminated, bright cone of light is called the Tyndall cone. Try to recollect that every time you go to a cinema hall, you're able to trace the path of the light beam from the projector. What you actually see is the Tyndall effect. A Tyndall cone formed due to the scattering of light by dust particles is seen in the movie hall. The Tyndall effect is observed only when two conditions are satisfied. First, the diameter of the particles of the dispersed phase should not be too small than the wavelength of the light used. This implies that this effect is observed when the dimensions of the colloidal particles are comparable to the wavelength of the visible light used. Secondly, the refractive indices of the dispersed phase and the dispersion medium should differ greatly in magnitude. The Tyndall effect was used to devise an instrument known as the Ultra Microscope by Zsigmondy in the year 1903. The instrument is used to detect particles of colloidal dimensions. In an ultra microscope, an intense beam of light is focused on a colloidal solution in a glass vessel. The solution is then observed in the microscope at right angles to the beam of light. The zone of light scattered by each individual colloidal particle is larger than the particle size. Therefore, a colloidal particle appears as a bright star against a dark background in constant motion when viewed through an ultra microscope. Thus, we can say that the ultra microscope does not render the actual colloidal particles visible, but allows the light scattered by them to be observed. It does not provide any information about the size and shape of the colloidal particles. The Tyndall effect also confirms the heterogeneous nature of colloidal solutions. Another important optical property of colloids is their color. Colloidal solutions are generally colored. The size, shape, and nature of the particles determine the color of a colloid. Larger particles absorb light of longer wavelength and therefore transmit light of shorter wavelength. For example, in a gold sol, if the particles are very fine, the sol is red in color, but when the size of the particles grow, the color changes to purple, then blue, and finally golden. The color of a sol also depends upon the manner in which the observer receives the light. For example, in reflected light, an aqueous solution of milk appears blue, whereas it looks red in transmitted light. Let us now learn about the mechanical properties of colloidal solutions. The continuous zigzag movement of colloidal particles in a dispersion medium is called Brownian movement. This random zigzag motion was first observed under a powerful microscope by the British botanist Robert Brown and is named Brownian movement after him. Brownian movement is independent of the nature of the colloidal particles, but depends upon their size and on the viscosity of the solution. The movement of colloidal particles increases with a decrease in their size and in the viscosity of the medium. Brownian movement is caused by the bombardment of the molecules of the dispersion medium against the colloidal particles of the dispersed phase from all sides with unequal and unbalanced forces. This movement opposes the forces of gravity and has a stirring effect, meaning that the colloidal particles resist settling rapidly to the bottom of the vessel. Hence, we say that Brownian movement is responsible for the stability of a colloidal solution. Apart from exhibiting color, the Tyndall effect, Brownian motion, and colligative properties, colloidal solutions also exhibit electrical properties. The properties that we will discuss in this module are electrical charge on colloidal particles, electrophoresis, electro osmosis, and coagulation of salts. Let us first discuss the most important electrical property, the presence of electrical charge. The particles of a colloidal solution possess a definite electrical charge, either positive or negative on them. Due to the presence of the same charge, they repel each other and do not combine to form larger particles. This keeps them dispersed in the medium, and hence, a colloidal solution is stable. All the particles in a solution carry the same charge. The dispersion medium has an equal and opposite charge. Based on the nature of the charge on the colloidal particles, colloidal solutions are classified as positively charged or negatively charged salts. Hydrated metallic oxides like Al2O3XH2O, Fe2O3XH2O, and Cr2O3XH2O, and basic dyes like methylene blue form positively charged salts. Starch sol, metal salts like copper sol and gold sol, metal sulfide sols like arsenious sulfide sol, and acid dyes like Congo red are examples of negatively charged salts. The electrical charge on colloidal particles may be due to several reasons. These include electron capture by the colloidal particles during electrodispersion of metals, preferential adsorption of ions from the solution, and the formation of an electrical. Let us discuss the most accepted reason first. The preferential adsorption of ions. Colloidal particles have the tendency to preferentially adsorb a particular type of ion from the solution. An ionic colloid preferentially adsorbs the ion common to the colloidal particles from the solution. For example, silver iodide precipitate adsorbs iodide ions from the dispersion medium if an excess of potassium iodide is used to prepare it. This results in the formation of a negatively charged colloidal solution. However, if an excess of silver nitrate is used for the precipitation of silver iodide, preferential adsorption of silver ions takes place, resulting in the formation of a positively charged colloidal solution. Similarly, a positive sol of hydrated ferric oxide is formed if ferric chloride is added to excess of hot water. This is due to the preferential adsorption of ferric ions. However, a negatively charged sol of ferric hydroxide is obtained when ferric chloride is added to sodium hydroxide. In this case, there is preferential adsorption of hydroxyl ions on the colloidal particles. In either case, the ions left out will give an equal and opposite charge to the dispersion medium and will remain in it. The positive or negatively charged colloidal particles of a layer attract oppositely charged ions from the dispersion medium, forming a second layer as shown here. These counterions are not absorbed on the surface of the colloidal particles, but exist in the solution. The combination of two layers of opposite charges around a colloidal particle is called the Helmholtz electrical double layer. The first layer is firmly held and is called the fixed layer, while the second or the outer layer is mobile and is termed as the diffused layer. The presence of opposite charges on the fixed and diffused layers of the double layer results in a difference in potential. This potential is called electrokinetic potential or zeta potential. Let us now discuss another electrical property of colloidal solutions, electrophoresis. The movement of colloidal particles towards a particular electrode under the influence of an electrical field is called electrophoresis. Electrophoresis helps establish the existence of electrical charge on colloidal particles. This property can also be used to establish the nature of the charge carried by the colloidal particles in a colloidal dispersion. The direction of movement of colloidal particles towards a particular electrode is governed by the nature of the charge on them. If the colloidal particles carry a positive charge, then they move towards the cathode when subjected to an electrical field, while negatively charged colloidal particles move towards the anode. An important application of electrophoresis is in sewage disposal. Let us discuss another electrical property, electro osmosis. If an electrical field is applied to a colloidal solution and a semi-permeable membrane is used to prevent the colloidal particles from moving, then the dispersion medium moves in a direction opposite to the direction in which the colloidal particles would have otherwise moved. This phenomenon is called electro-osmosis. Let's define it. Electro-osmosis is the movement of a dispersion medium under the influence of an electrical field when the movement of colloidal particles is prevented by a suitable membrane. Under the influence of an electrical field, the colloidal particles and the dispersion medium both have a tendency to move towards the oppositely charged electrodes. But the semi-permeable membrane does not allow the passage of the colloidal particles. The dispersion medium, however, can pass through the membrane and therefore its movement takes place. Another very important property of colloids is their coagulation, flocculation, or precipitation. You already know that one of the factors responsible for the stability of lyophobic colloids is the presence of charge on colloidal particles. However, if the charge is destroyed, they are free to come near each other to form larger molecules. These larger molecules aggregate or coagulate and then settle down under the force of gravity. This phenomenon is called coagulation or precipitation of the sol. The coagulation of a lyophobic colloidal solution can be achieved in a number of ways. One method is electrophoresis. You know that the colloidal particles in a colloidal dispersion move towards a particular electrode under the influence of an electrical field. If the process is carried over a prolonged period of time, then the colloidal particles get discharged at the oppositely charged electrode and get coagulated. Another method used to bring about coagulation is by mixing two oppositely charged sols. Mixing equal proportions of two oppositely charged sols neutralizes the charges either partially or completely, and thus causes the colloids to coagulate. For example, if equal proportions of a positively charged sol of hydrated ferric oxide and a negatively charged sol of arsenious sulfide are mixed. Then, the coagulation of both the sols takes place. This type of coagulation is called mutual coagulation. A sol may also be coagulated by simple boiling. When a sol is boiled, the adsorbed layer on the colloidal particles is distributed because of the higher number of collisions with the molecules of the dispersion medium. This reduces the charge on the colloidal particles and ultimately leads to precipitation. Arsenious sulfide sol undergoes coagulation on boiling. The coagulation of a sol can also be brought by persistent dialysis. You already know that traces of electrolytes are essential for the stability of colloids, since they get absorbed on the surface of colloidal particles by giving them charge. If the electrolyte is removed completely by persistent dialysis, then the colloidal solution would become unstable and undergo coagulation. The most important and useful method of coagulating sols is by adding an electrolyte. While traces of electrolytes are essential for stability, adding substantial amounts brings about the precipitation of colloids, as it completely neutralizes the charge on the colloidal particles. The ion responsible for causing coagulation is the one that carries a charge opposite to that present on the colloidal particles, and is known as the coagulating ion. For example, a positively charged sol gets coagulated by the negatively charged ions of the electrolyte that is added. The coagulation behavior of different electrolytes can be explained on the basis of the Hearty-Shoals rule. The rule states that the greater the valence of the flocculating ion added, the greater is its power to cause precipitation. Let's see an example. The coagulating power of different cations to coagulate a negative sol follows the order aluminium 3+ ions greater than barium 2+, greater than sodium+. This shows that tripositive ions are more effective than dipositive and unipositive ions. Similarly, the coagulating power of different anions to coagulate a positively charged sol decreases in the order FeCN6 4 negative greater than PO4 3 negative greater than SO4 2 negative greater than Cl negative. The coagulation of a sol by an electrolyte does not take place until the electrolyte added has a certain minimum concentration in the solution. The minimum concentration of an electrolyte in millimoles per liter required to cause a sol to precipitate in 2 hours is called its coagulating value or flocculation value. It is important to note that the smaller the flocculation value, the greater is the coagulating power of the electrolyte. You can see from the table that the aluminium 3+ cation and the FeCN6 4 negative anion have extremely low values of coagulation power. Therefore, They exhibit greater coagulating capacity as compared to other ions in their category. Lyophilic salts, on the other hand, are much more stable than lyophobic salts and do not get coagulated easily under similar conditions. The two factors responsible for the stability of lyophilic salts are the existence of the same charge on all the colloidal particles and the extensive solvation of the colloidal particles of a lyophilic sol. A lyophilic sol can be coagulated either adding an electrolyte or a suitable solvent. A higher concentration of an electrolyte is needed to coagulate a lyophilic sol than is needed to coagulate a lyophobic sol. When solvents like alcohol or acetone are added to hydrophilic salts, the colloidal particles get dehydrated. Under this condition, a small quantity of electrolyte is able to bring about coagulation of the hydrophilic sol. Let us now discuss the protection of colloids. You already know that lyophobic sols, such as metal sols, are very susceptible to coagulation or precipitation. The process of protecting them from coagulation is referred to as protection of colloids. It has been observed that in the presence of certain lyophilic colloids, lyophobic sols acquire greater stability. They do not get coagulated easily when an electrolyte is added. A layer of lyophilic sol particles around the lyophobic sol particles prevent them from coagulating. The sheath of solvent molecules of the lyophilic colloid prevents the particles of lyophobic colloids from aggregating at low electrolyte concentrations. For example, adding gelatin, a lyophilic colloid, to gold sol, a lyophobic sol, protects the gold sol from getting coagulated if a small amount of sodium chloride solution is added.